Now, in the last video, we looked at doing a confidence interval for the difference between two proportions. In this video, we'll look at doing a hypothesis test for the difference between two proportions. Now, the setup is the same. We have our formula for the standard deviation, which if we substitute in our sample standard deviations, that would be the standard error. We went over this in the last video. The assumptions and conditions are the same for both the confidence interval and for a hypothesis test. We need to have data that is collected using some randomization procedure. It's no more than 10% of the population. The two groups are independent of one another, and there are at least 10 successes and 10 failures in each of the groups. So if that's the case and our sample sizes are large enough, then that sampling distribution of the difference between the proportions will have a mean at the difference of the population proportions and the standard deviation given by the formula we talked about. The conditions are the same whether we're talking about a confidence interval or a hypothesis test, that randomization, 10%, success failure, and the independent samples test, okay? Now, because we're hypothesizing the proportions are equal, we pool them to find our p hat pooled, which is this formula here. And then the standard error of the pooled can be calculated thusly, and our test statistic is like so. Again, the good news is as the last couple of videos, you guys aren't going to have to calculate these by hand. We're going to let the computer do everything for us, but you do need to remember how to find that area under the normal model and use it to find the p-value. We'll see how to do it with the test directly, but if you're finding your critical values, you again have to find those using your inverse z key this time. All right, so let's look at an example with the textbook. Problem number 24 is what I'm going to do. So right over here. So a study published in the Archives of General Psychiatry examined the impact of depression on a patient's ability to survive cardiac disease. Researchers identified 450 people with cardiac disease, evaluated them for depression, and followed the group for 4 years. Now, here's where we break it down into two separate groups. 361 patients had no depression, and 67 of them died. And then 89 patients had depression, and 26 died. So among the people who suffer from cardiac disease, we want to know, are depressed patients more likely to die than non-depressed patients? So let's go back over here and let's write down some of our basic information in working with this problem. So first of all, we're going to let P1 be the proportion of people without depression who died. And then P2 is our proportion of people with depression who died. So now notice that our P1 value then is going to be the 67 out of the 361 who died during the study time. And our P2 is going to be the 26 people with depression, or 26 people who died out of the 89 who had depression during the study period. And that's the total of the 450 people divided up into two groups. Okay, so now that we have the basics down, let's look at the questions. What kind of design was used to collect the data? Well, first of all, we identified these 450 people, divided them into the categories, and followed them forward in time. If I'm following them forward in time, that is a prospective study. Okay, going forward in time is a prospective study. All right, so now our hypotheses. So with our hypotheses here, notice that we're saying, by the way, first of all, are patients who are depressed more likely to die than non-depressed ones? So in other words, I would expect the proportion of the depression patients to be higher than the proportion of the non-depressed patients. So when I'm writing down my hypotheses, My null hypothesis is that the two groups are equal. So P1 minus P2 would be a 0, or equivalently, I could have written P1 equals P2. But now the alternative hypothesis I want is that the proportion of people who had depression minus the proportion of people, or the proportion of people without depression minus the proportion of people with depression would be negative. So in other words, we're wondering, is this bigger than this one, right? If so, then when I subtract them, it would be negative. And that's what we hypothesized, that people who had depression were more likely to die, right? So that's the way we're setting up our hypotheses. Okay, let's go back to the problem for a minute. Now, are the assumptions and conditions necessary for inference satisfied? So first of all, we need to make sure that it's randomized. Now, it doesn't say anything in the study about whether that's the case. So we would have to say, we would assume that these 450 people were randomly selected in some fashion. The 10% condition, certainly 450 people is less than 10% of all people with cardiac disease. And then that's our 10% condition. Our two groups are independent. The patients with depression are separate. They have nothing in common with, they don't overlap with the patients in the depression group. You're either in one or the other, and they don't influence one another. So those are independent groups. And then the 10 successes and failures. Now notice that 26 is our lowest number here. That's more than 10, right? And then 89 minus the 26 would certainly be more than 10. So our success failure condition would be satisfied. All right, so now let's test the hypothesis and state our conclusion. So to test the hypothesis, we're going to come over here to our calculator, and we are going to go to, don't do it, don't open up. It's not cooperating today. Let's just move. Okay, there we go. Stat, and then go over to the tests, and then I want to go down to the 2 proportion Z test, and that is option 6 here, 2 proportion Z test. So we're going to hit enter, and we're going to enter our data. So our X1 we said was 67 successes out of our 361 people without depression, and our X2 is the 26 people who died out of our 89 people with depression. And then we said that our hypothesis is that P1 is less than P2. Calculate. And here's what we get. All right, we get a z-value of negative 2.22. So let's write that down, negative 2.22. And the p-value that goes with that, we're going to go back over here to the calculator. The p-value is this 0.0131. 0.0131. Okay, now notice this p-value is less than alpha, which I don't remember if it was stated in the problem. If not, it's 0.05. But this value is less. So we reject the null hypothesis, right? That's our decision. Now, why are we rejecting the null hypothesis? Because this probability of occurrence is smaller than our alpha value, okay? Once we reject the null hypothesis, that's rejecting the statement that the 2 proportions are equal, we would say we have evidence to believe, let's try to get that writing, we have evidence to believe the death rate for people with depression or cardiac patients with depression who die within 4 years Okay, so that is our conclusion for our study there, right? Test the hypothesis and state the conclusion. Explain in context what our p-value means here. So now that p-value is the 0.013. So that means that if the two proportions are equal, if there is no difference in the proportions, we will see an observed difference this big or larger only about 1.3% of the time by natural sampling variation. Okay? That's what that 0.013 means. Now, if your conclusion is actually incorrect, which type of error did you commit? Do you remember our discussion of type 1 and type 2 errors? That would be an example of a type 1 error. Okay, guys, this should give you enough information to complete the hypothesis testing. Be sure to email me if you have any questions.